Okay, so I asked you to think about a deep water wave that has this dispersion relation, omega equals square root of g times the wave number k. So to find the phase velocity here, right, the phase is omega over k, so that's root gk divided by k, or square root of g over k. So the group, on the other hand, is given by d omega dk. And so we've got the root g, but then we have to take the derivative. So I'll write that as root g times d dk root k. And hopefully you remember how to do that from calculus. We end up with 2 square root k downstairs, or 1/2 root g over k. So we see that a wave packet in this case would move half as fast as individual sinusoidal crests and troughs. But notice the interesting thing here, right? So notice that, right, that the phase velocity, they both depend on k, or on the wavelength. So in this case, right, so for so longer wavelengths, right, are associated with a shorter k, because k, the wave number is 2 pi over my wavelength, so smaller k. Okay. And a smaller k means that there's a larger phase velocity. Interesting. So what I'll do in a moment is I'll cut away to some videos where we can actually see this effect and what this means for actual waves in water. Okay, so there's one more thing that I want to look at. So you had just worked out this whiteboard problem for the dispersion of deep water waves. Well, let's look at a real-life example. So I apologize that this video is in German, but it's the best video that I've found, and I'll play it live for you now so that I can try to provide some translation. If there are any native German speakers in the class, please feel free to correct my Google Translate attempt at getting the German right. So, just dispersion by Wasserwellen, dispersion of water waves. So what you're seeing here, if I pause this, is they've put a mirror on the shore, and what you can sort of see is that I guess it's either the crests or the troughs of the wave, it's not quite clear, are these black lines that are reflected here. And as we've talked about, right, those crests and troughs move at the phase velocity, that's Phasengeschwindigkeit. So a little bit of commentary, what they've just done by dropping a stone in the water is to basically excite a bunch of waves of a whole range of frequencies and wavelengths. It's kind of like analogous to if you like take a guitar string and you pluck it into like a triangle, you're going to excite lots of different standing waves, the harmonics. So we'll talk a little bit more about that and Fourier analysis later on, but that's sort of the idea that dropping the stone has excited lots of different sinusoidal waves. And what this is asking is, does it look like the wavelengths that are coming to the shore are getting shorter as time goes on? So you can go and rewind that if you want to see it again, and so we'll see that some still frames now. And I think you can, in fact, see that as time goes on, the it's shorter wavelength waves that are reaching the shore. So this is a dispersion for water waves. It's different from the one you looked at in the example because there is surface tension of the water taken into account, which is responsible for what's going on down here. And this is the wave speed as a function of wave length. So it is different than what we've talked about in class, but you still get the general idea, right? So what what this graph is showing, right, is that longer wavelength waves move faster. So, and I think that's what they're going to show here. So longer waves, shorter waves, faster, schneller is faster, langsamer is slower. And so you can see here, right, that because the longer wavelength waves move faster, they're the ones that reach the shore first. And and that's the important thing to take away from this video, that the dispersion relation that you just looked at for water waves really does have some real world applications. So today we've practiced applying the Heisenberg uncertainty principle with an estimate. We have looked in more detail at wave packets and how they move. And we talked about the difference between phase velocity, which is the speed at which individual crests and troughs move, and group velocity, which is the speed at which a wave packet moves. We've looked at that for both quantum waves as well as for a more concrete example with water waves. Next time, what we'll talk about is momentum. We haven't yet talked about how to calculate momentum expectation values, so we'll do that, and that will allow us to rigorously apply the Heisenberg uncertainty principle once we figured out how to calculate delta px, the uncertainty in momentum, and then we'll be able to go and apply that to actual wave functions. See you next time.